Welcome to Paramount Plus number 121, and today we're talking about how different geometrical shapes affect how good a boundary layer trip is at tripping a boundary layer. So a boundary layer trip, is typically a small piece of plastic that runs along a surface. And what this does is it turbulates the flow. So I'll quickly draw it here. And if you're listening to this on Spotify, you can always watch the video on Spotify and or on YouTube. So let's say we have a surface here and we have the flow going over it. Then we have at some point on the surface this little protuberance just jutting up, and it can be of any shape really, as we'll get into how these shapes do affect how well this boundary layer trip does trip the boundary layer. Anyway, so the flow comes along and it's in the boundary layer, then it hits this thing and it gets redirected up, and there's a lot of turbulence now that occurs around this trip. And what this does is it accelerates the onset of turbulence. So then all these turbulence that we have will break down, and then the boundary layer will now become turbulent. So that's the general function of a boundary layer trip. But as we're going to be covering, are different shapes better at doing this and or worse at doing things? So depending on what we're looking for, sometimes a shape will be better, but other times it'll be worse. So to look into this, we're going to look at a paper called Comparative Study on the Aerodynamic Performance of Airfoils with Boundary Layer Trips of Various Geometrical Shapes. And this is open access, so you can find it in the link description. And this paper is going to be covering small-scale wind turbines, so the blades on these things. So let's get into it. They say, so small-scale wind turbines can be used even in remote locations as independent or as microgrid feeders where electricity from conventional power resources are not feasible. And these typically work under low Reynolds numbers, so around about 100,000 or less. So this is a very important Reynolds number range because this is effectively in the transitional regime. And what happens here is laminar separation bubble formation is a common aerodynamic phenomenon on these small-scale wind turbines at these low Reynolds numbers. So laminar separation bubbles I've covered in a few other podcasts. I'll just go briefly over it again. So what happens is you have the flow coming over, and then as it starts to, it's still laminar, but as it starts to sort of get a little bit more poorly behaved, like there's a little bit more turbulence, it will then start to separate. And then during the separation phase, it will transition to turbulence and then it'll reattach. Then inside this bubble in its bubble section, we have this recirculation zone. So this bubble is now pretty much cut off from the rest of the free stream flow. And this means that this is just a dead pocket. And this is potentially beneficial, but potentially detrimental to the performance of your object, depending on what you want. And we'll cover in this podcast some ways that it is detrimental. So laminar separation bubble formation can occur typically at this Reynolds number range, which is between about 50,000 Reynolds number and 200,000 Reynolds number. So it could be a little bit more, could be a little bit less, depending on the roughness of the surface and or the turbulence density level. So during low operation, the low energy laminar flow over the blade may not withstand this adverse pressure gradient that occurs over a blade. Consequently, the flow separates from the blade surface, promoting reverse flow with mixing and momentum exchange with the adjacent flow field. Finally, the flow converts to turbulent and regains sufficient energy and continues as an attached flow. This is the LSB described. This region is, in this recirculating dead air zone, they call it, is the termed LSB. We're going to be using LSB for laminar separation bubble from now on, that acronym. So let's move on with what they're looking at. So the main effect of an LSB is an increase in the boundary layer thickness, effectively, which increases pressure drag due to this pseudo thickness over the airfoil and loss of lift. So why does that occur? So instead of, let's say we have this object, which is typically, let's say 1 meter thick or whatever it is. Let's say 10 centimeters thick. Now we have the laminar separation bubble, which has its own thickness. And this is effectively an additional thickness because the flow going over this LSB is not interacting with this LSB. So this LSB is cut off, as I mentioned earlier, and it could be, let's say, 1 centimeter thick. So now the entire thickness of this object is now 11 centimeters thick, giving a slightly thicker object than just the 10 centimeters. So that's what they mean here. So by controlling the LSB formation on wind turbine blade performance can be improved. The premature transition of the laminar boundary layer into a turbulent boundary layer using any external means such as flow control techniques is the most effective method of LSB elimination. Passive and active vortex generator methods are being developed and are proven to be successful in reducing the effects of the LSB over the low Reynolds number of airfoils. Boundary layer grits, boundary layer wires, boundary layer trips, and surface dimples are some of the passive flow control devices used to control LSBs. So these are all similar ways of doing a boundary layer trip effectively. So boundary layer grits is where you just like roughen the surface before the where you want to transition, obviously. That surface roughness then introduces more turbulence into the flow and hopefully breaks down into three-dimensional turbulence, and you get a turbulent boundary layer. Boundary layer wires are very similar to boundary layer trips. It's just a wire going across to trip the boundary layer effectively. And surface dimples, again, are very similar, where you just have now effectively a rougher surface because you have all these dimples being taken out of the surface, and now it's going to be producing turbulence. And depending on how big the dimples are, sometimes that can produce vortices around like the edges, and that can result in turbulent boundary layer. So using the use of mechanical boundary layer trips like trip wires, plane trips, zigzag tape, etc., is the most effective method of LSB elimination currently used. So tripwires, plane trips, and zigzag tape. Zigzag tape is one of the most common ways of tripping a boundary layer. It's just as you'd think, it is a zigzag tape. So you just have a tape that zigzags along, and the flow comes straight onto it, and you get not only trips but sometimes again vortices coming off of that, which help to turbulate the flow. So some researchers studied the effects of the boundary layer trips, so BLTs. BLT, I'm going to be using for that acronym, which is similar to the bacon, lettuce, tomato sandwich, so that's easy to remember. So the effects of BLTs located at various coordinate locations on a Clark Y12 airfoil that runs numbers between 62,000 and 209,000. They reported a significant increase in drag than the lift for the airfoil with BLTs at higher Reynolds numbers. The BLT improved the performance in the low Reynolds number range only up to about 135,000. Above that, it didn't so much. And the reason for that is because once you get to a higher Reynolds number, the LSB doesn't really form as much. And actually the zone that the LSB covers is smaller as well. So some other researchers experimented in low Reynolds number ranges from 40,000 to 120,000 on an E423 airfoil, and found that the tape trips improved the lift at low angles of attack and higher Reynolds number ranges, and reduced the drag at only low Reynolds numbers. So this is interesting because the effects of boundary layer on laminar separation bubbles on the lift production of an airfoil can be varied. So often they will actually increase the lift production. So if you go to a thick airfoil, if I draw the lift curve slope, so I have the angle of attack on the x-axis and the lift coefficient on the y-axis, typically the lift curve slope will be linear, and then you'll get the regular stool pattern. When you have an LSB forming, you get, let me change colors here, you get the similar lift curve slope to begin with, but then as we go a bit higher, we'll then start to go up in the lift curve slope, and then we'll get a stall pattern. So the reason why we get a sharper increase here is because of the LSB. And the reason why is because now we've effectively cambered the airfoil and made it thicker. So we're now moving this lift curve slope up in this. So if you were to plot this back in a linear fashion, you would then intersect the lift curve slope, the lift coefficient axis at a higher lift coefficient, which is indicative of a cambered airfoil. Because cambered airfoils do produce lift at 0 degree angle attacks, whereas uncambered airfoils, symmetrical airfoils, produce no lift coefficient at 0 degree angle attack. So that's why we can increase the lift coefficient of airfoils under certain situations. Other situations, not so much. They say here that improved drag and the reduced lift is reported for most cases by Traub and others. It proves that the BLT performance, or boundary layer trip performance, depends on the type of airfoil, and the net advantage depends on the relative benefit between the lift and drag coefficients, and hence the lift to drag ratio should be studied as a performance parameter. So that should be something that we measure different BLTs by. BLTs work better when the flow transition completes, before the boundary layer reattachment point. So in other words, when you get the flow detaching from the surface, by the time it reattaches, it should have completely turbulated, and now it's reattaching as a turbulent boundary layer. They're saying BLTs work best under this situation. Complex trip geometry such as 3D, zigzag, and other multiple trips produce little benefit over single 2D plane trips. Effective drag reduction requires thin BLTs. The 2D trips are more acceptable because of its simple structure and ease of fabrication. Hence, a detailed study on the plane 2D trip of different shapes, namely the isosceles triangle and right angle triangle, is carried out in this paper. Two-dimensional numerical simulations are carried out to study the aerodynamic performance and the flow structure of an airfoil of an E216 type with an isosceles triangle BLT, a right-angled triangle BLT for 4 degrees, 6 degrees, and 8 degrees, and at Reynolds numbers of 100,000. They're using the Mentor's gamma theta turbulence model for RANs, and performance evaluation is done for two chord-wise locations of the trip. So they're placing the chord at either 70% downstream of the leading edge or 10% downstream of the leading edge. And they're using different trip heights of 0.3 millimeters, 0.5 millimeters, 0.7 millimeters, and 1 millimeter. The results are compared with the author's published results for the baseline and airfoils with rectangular trips to ascertain whether the geometry of the trip has any effect on the LSB. So looking at three different types of trips effectively, a right angle, isosceles triangle, and then the rectangular trip to see which one is best, and at different heights of these trips and at different locations on the airfoils, from 10% from the chord from the leading edge and 70% from the leading edge. So intermittency, which is one thing that they're using for their RANS model, is a pretty cool idea effectively. So they say the intermittency concept was introduced by Darwin and others to predict transition, and its further development by Mentor and others made it possible to use RANS models for phenomena such as an LSB formation. So intermittency is effectively like a pseudo parameter to determine how much of a boundary layer is turbulent or not. So if you had an intermittency of 10%, it means 10% of the time the boundary layer at this point is turbulent. If it's 90%, it means that 90% of the time the boundary layer at this point is turbulent. So that's effectively what the intermittency means. And it's a pretty cool idea. It's a very interesting way of trying to figure out something which is inherently difficult to figure out with a RANS model. It's going to be inaccurate, but they find it's kind of like fuzzy logic where the RANS approach of determining when a boundary layer is turbulent is dodgy. This intermittency idea is dodgy, but because they're both dodgy, they kind of like cancel out the dodginess, and now it works out quite well. So the methodology, the airfoil E216 selected for the study is a cambered, low Reynolds number airfoil suitable for a small-scale wind turbine. A 2D view of the airfoil is shown in Figure 1. It is a thin airfoil with a maximum thickness of 10.4% of the chord, and this occurs at 26.2% downstream from the leading edge. The camber is 4.7%, and it occurs at 59% of the downstream from the leading edge, and the trailing edge is quite thin as well. So it's arguably a fairly thin airfoil. So the free stream inlet velocity is set to 10 meters per second, which corresponds to a Reynolds number of 100,000. And as we mentioned earlier, they're looking at three different boundary layer trip shapes. They have a rectangular boundary layer trip, a right angle boundary layer trip, and an isosceles triangle one. So what is the difference between these two? For those of you listening to this, so the right angle triangle, imagine you just get like a box and then you put it onto the surface, and that's the trip. They shrink it down, obviously. So it's like 1 millimeter high, but that's the same kind of geometry. The right angle triangle is now you have the surface, and you put a slope on like one little bit, and then you suddenly have a drop off at the end, and it goes back to the regular surface height. That's the right angle triangle boundary layer trip. The isosceles triangle is now it's just a symmetrical triangle that you place onto a surface. So the surface is, itself is the third side to the triangle, and then you just have that peak popping up where each side is the same length, and that means you have the same angles when they meet the table or the surface, and that is producing your boundary layer trip. The reason why they're looking at three different geometries, and quite different geometries here, because they want to see how this affects not only the lamp separation bubble formation, but also the lift and drag productions. So the results, and actually let's talk about the results of discussion here. So we have the velocity, but actually we're not going to talk about the results of discussion first. We're going to talk about the grid independent study. So Figure 6 shows the grid independent study is conducted with 5 sets of meshes ranging from 10,000 to a 610,000 mesh CFD. So this is for the baseline, the right angle triangle, the rectangular boundary layer trip, and the isosceles triangle boundary layer trips. These are all of 1 millimeter trip heights. The same pattern mesh is used for respective trip shapes with all other trip heights. The lift and drag coefficients are the parameters checked for the grid consistency. The simulations are carried out at an angle of attack of 6 degrees, and the results for the baseline test are shown in figure 6. After around 475,000 grid cells, there is no significant variation in the lift coefficient, and hence it is considered as appropriate mesh size for further simulations for the baseline mesh. So the grid independent study shows that going to like 600,000 cells doesn't really change the drag very much. So 475,000 cells is good enough. So let's talk about now the results and discussion. Let's talk about the velocity vector plots. So in figure 7, the flow structure over the airfoil with a trip for a trip height of 0.7 millimeters at an angle of attack of 4 degrees for the locations of 10% downstream and 17% downstream are shown in figure 7 and figures 8. The boundary layer trips enhance the boundary layer momentum exchange, resulting in energized flow and the elimination of the LSB. Let me zoom in a little bit so you can see this a bit better. So we can see the boundary layer trips just here, and let me scroll down a bit, here. And behind there, we get a little bit of recirculation zone, but the LSBs are largely, I'll zoom out a little bit more here, are largely eliminated. So a recirculation zone is observed just downstream of the BLT, where the transition of the boundary layer from laminar to turbulent occurs as reported in other studies. The main aim of this study is to reduce such a dead air zone, which is observed for the rectangular trip. The velocity vector plots shown in the isosceles triangle trip introduces the longest recirculation region compared to the other 2 types for both of the cases, i.e. trip at location 1 and location 2, so 10% downstream and 17% downstream. But the shortest recirculation length is observed for the right angle trip. So from this particular perspective, the right angle trip fulfills the required objective of shorter recirculation zone is created for the trip with a vertical rear face than that with a slant rear face. So what does this all mean? So what they're trying to figure out is which boundary layer trip can reduce the recirculation zone the most. The rectangular trip, the isosceles triangle, which is the symmetric triangle on the surface, or the right angle triangle. And they found that the right angle triangle is the best. The rectangular triangle is not too bad, but the right angle triangle beats it just slightly. And the reason why is because both of these shapes, they have that sharp drop off at the back. So the flow just comes down hard to the surface quite quickly. For the isosceles triangle, where the flow, it goes over the triangle, but then the back surface is not that sharp. That means that there's not as much of a low pressure there because you don't have this void that just suddenly occurs. It occurs more gradually. So that means that the flow is not being sucked down nearly as quickly. And that means that you have a recirculation zone which is much greater. So that's just all what that means here. So the LSB is eliminated by all 3 types of BLTs at both locations. And similar results are obtained for angle of attack of 6 degrees and 8 degrees. Okay, so what about the pressure coefficient distribution? So we looked at the streamlines effectively, but the pressure coefficients are quite interesting because they show you effectively how much lift is being produced over the surface. And the pressure coefficient distributions are plotted in figures 9 and 10 for the trips of 0.7 millimeter heights with angles of attack of 4 degrees, with the trips located at locations 1 and 2, so 17% downstream and 10% downstream. The suction peak of all the trip airfoils lies below that of the baseline airfoil. So in other words, we have the baseline airfoil, which is in black here, and as we expect for both locations of the trips, which obviously the baseline airfoil doesn't have any trips, but for both figures we can see it here, that the pressure coefficient sort of drops a little bit more than what you'd expect, around about 70% from the leading edge, and then it drops off again. And that's this LSB forming right here. None of the boundary layer trips exhibit that peak there. So they're all quite smooth, which indicates that the LSB has been eliminated from each one of these trips. What's more, each one of these trips results in a significant reduction in the pressure coefficient very close to the leading edge, effectively where they are. So they cover this as well. They say suction peak of all the trip airfoils lies below, it may be concluded that the LSB is eliminated with the BLT as there is no observable pressure plateau on the pressure coefficient distribution. But a sudden jump in the pressure coefficient on the suction surface of an airfoil downstream of the trip due to the flow obstruction caused by the trip is observed for all three types of trips. So that's this peak here that we get for each one of these boundary layer trips. This is evident from the vector plot also in the form of the recirculation region. The reattachment point of the boundary layer after recirculation for the rectangular and the right angle trips are almost the same, but the isosceles triangle is a little bit further downstream. This is due to the geometrical peculiarity of the trip. Unlike the rectangular and the right angle trips, the isosceles triangle trip has an extended, gradually declining surface after its maximum height. This surface makes the recirculation flow to attach gradually to the airfoil surface, resulting in an extended reattachment length. And the CP distribution, so the pressure coefficient distribution for the airfoil with the the right angled trip, is flatter than that for the airfoil with the other two types of trips. So the isosceles triangle not only has this slightly lower peak in this low pressure zone, but it also takes longer for it to dissipate back to what you'd expect over the airfoil and meet the regular baseline situation here. Now, when the angle of attack is increased to 6 degrees, which we can see in figure 11 and figure 12, the suction peaks of the tripped airfoils vary significantly. So we still get in the baseline airfoil this LSB forming, which you can see from this peak here around about 60% of the chord downstream or from the leading edge. And this is very normal. As you increase the angle of attack, this LSB moves towards the leading edge. None of the tripped airfoil surfaces exhibit this LSB. The suction peak is highest for the right angle trip and lowest for the isosceles triangle trip, as shown in figures 11 and 12. So we can see we still get these peaks in the low pressure around about 20% of the chord downstream, but the isosceles triangle is not exhibiting nearly as high as the right angle trip, as the rectangular trip, and it takes longer for it to dissipate back to what we expect. The suction peak for the baseline airfoils lies above that of the tripped airfoils, though. So that would indicate that potentially you're increasing the lift, like the baseline airfoils has a higher lift coefficient compared to the other tripped airfoils. And complete elimination of the LSB is achieved at this angle of attack, as is represented by the smooth suction surface of the pressure distribution around the 60% chord range. At an angle of attack of 8 degrees, there is a large deviation in the magnitude of the suction peak pressure for the tripped airfoil, as well as from each other, as shown in figures 13 and 14. So not only do we have now this LSB forming for the baseline trip for the baseline airfoil, and that's getting closer to the leading edge, we also have now none of the boundary layer trips forming the LSB as expected, but also the maximum, the minimum pressure coefficient, this peak here, is now becoming more and more different among the different trips. And not only that, so we have the rectangular trip and the isosceles trip. They kind of follow each other somewhat similarly. They're still a little bit different, but the right angle triangle trip is very different. So towards the leading edge, the pressure coefficient is much lower than the other ones. Not only that, but after we get past the trip, the pressure coefficient is still lower. So this region here is going to result in a much lower lift coefficient because we're not producing as much lift. The pressure difference between the suction surface and the pressure surface is much smaller in this zone, near the leading edge, compared to the other airfoils with these trips and no trip. So this would indicate that we would get a lower lift coefficient production. And if in location 2, we still get the same thing. So that's interesting how this right angle triangle trip is not nearly as good in terms of lift production at this higher angle attack compared to the other two trips and the baseline trip and the baseline airfoil. What's more interesting is, as well as we get to location 2, which is where we have the boundary layer trip at 10% from the leading edge, the baseline airfoil produces a lot more lift than the tripped boundary layer airfoils. And that's probably due to this increased thickness, I would imagine, to some extent. I'm not sure because we don't have the flow vis for this, but potentially due to the LSB increasing this thickness, as I mentioned earlier, where we have the airfoil, and then we have the LSB forming over the top, and this is effectively additional thickness that we add to the airfoil's thickness. So that would potentially increase this lift production here. I'm not too sure though, because we haven't got this flow vis for it. So we can conclude this podcast. We'll go into the next podcast, the effects of these boundary layer trips on the lift drag and lift to drag ratios, as well as a few other things. But here we've just looked at what these boundary layer trips do to the pressure coefficients and to the LSB, and also what LSBs are and the boundary layer trips. So that's the end of this podcast. Make sure to like, subscribe, and if you want to get better at CFD and or theory yourself like this, check out our courses in the link section. And I'll see you next podcast. Peace out, amigos.